Up to this point, we exclusively discussed discrete random variables. Here's an example, again, randomly selecting an integer from 1 to 10. Obviously, we have 10 possible outcomes, 1, 2, 3, etc., up to 10. And if we assume that each have equal probabilities, each then would have 0.1 probability. But the key thing about this random experiment is obviously that the possible outcomes are discrete. We can list them, we can refer to them separately. Okay, so they are discrete values. The sample space is discrete, therefore this produces a discrete random variable. On the other hand, what if we are selecting a real number in the interval from 1 to 10? Not separate integers like 1, 2, 3, 4, etc. Now, it is possible to select any number, any real between 1 and 10. For instance, 3.5 is an option, 7.67 is another option, 3.72 is another option, etc. It doesn't even have to be a rational number. For instance, pi or e are all valid outcomes here because they are in the interval 1 to 10. Okay, so this is an example of a continuous random experiment because the sample space now is this interval, okay, and it's not a discrete set. You cannot separately list all possible outcomes here. It's a continuum. So the sample space is a continuous interval, and therefore the random variable produced through this random experiment is what we call a continuous random variable. Now, when we deal with such sample spaces, when the sample space is uncountable, okay, the equiprobable outcomes apply to intervals rather than specific points. So we have discussed this earlier very slightly, but you recall the approach here. The equiprobable outcomes approach now, rather than applying to specific outcomes, it applies to intervals. The size of the interval is going to be, the probability of the interval is going to be proportional to the size of the interval. So here, our sample space is the interval from 1 to 10, which means the interval has a total length of 9. Okay, so we are going to assign, obviously, 1 to the probability of the sample space itself. That's one of the Bayes rules. And then you can find the probability of any interval based on this approach. So the probability of the outcome being in the interval 1 to 2 would be 1 over 9, because you see this is 9 over 9. The length of the interval is 9, and its probability is going to be 1. Therefore, a unit length of interval will correspond to a probability of 1 over 9. So whatever the length of the interval, if you multiply it 1 over 9 in this example, you will get the probability of this interval. For instance, the interval from 3 to 8 has a length of 5, which means the probability of this interval, or probability of the outcome being in this interval, is 5 over 9. Now, what about this one? This is tricky. The length of this interval is 5, but the probability of the outcome being in this interval is not 5 over 9. Why? Because the entirety of this interval is not in the sample space. There is an overlap, but it's not entirely inside the sample space. So this is -1, this is 1, say this is 10. This is my sample space. And let's say 4 is here. This is the interval. And you see there is an overlap here, but this part is not in the sample space. So the outcomes will not be in this part of this interval. So actually, it reduces to this interval here from 1 to 4. and therefore the probability of the outcome being in this interval will be equal to 3/9 because the size or the length of this interval is 3. So what about specific points? In discrete random variables, we dealt with outcomes that are discretely specified. In our previous example, we had 1, 2, 4, 6.5, and 7. So how about that in this context? In a continuous sample space, for instance, in this example, what would be the probability of the outcome being exactly 4? Okay, so being exactly 4 means you are in the interval 4 to 4, because that's the only single point in this interval, which has a length of 0, and therefore the probability of this specific point is 0. And this is true for any value, any specific value you can think of, such as this one. It will have a probability of 0. Now, this could be a bit misleading, and I would like to emphasize this point here, especially with continuous random variables. A probability of 0 does not mean it's impossible. Okay, this point is very important. An event having a probability of 0 is not impossible. It may occur, but probability 0 means it's highly unlikely. Now, an example to this would be the following. Consider a die. Obviously, a normal die has 6 faces, and assuming it's fair, each side would have a probability of 1/6. Now, modify this die. For instance, there are special dies for playing some board games, which has many faces. Let's say you have a die with 24 faces, in which case, assuming again it's a fair die, the probability of each face will be 1/24. Now, assume that you have a die with n faces. Again, assuming it's a fair die, obviously the probability of each face will be 1/n. And when you take n to infinity at the limit, your die, your, let's say, a conceptual die, becomes a sphere. Let's say you throw it, okay, and each face now actually at the limit becomes a point. Now, when you throw, the probability of each of the faces becomes 0. Okay, so this is a little bit hard to grasp, but the probability of each specific point becomes 0. But when you throw it, obviously, one of them is going to be the outcome. Okay, so this might help you a little bit. The probability is 0, but that doesn't mean it will not occur ever. It doesn't mean the event with a 0 probability is impossible. Okay, very important point, especially with continuous random variables. An event having a probability 0 is not impossible. Okay, probability 0 is a special case. Obviously, if something is impossible, it would have probability 0. For instance, our discussion here, any outcome between -1 and 1 is impossible because it's outside of the sample space here. Therefore, the probability you assign to that should be 0 because it's impossible. But it doesn't go the other way. If you find out that the probability of an event is 0, you cannot automatically deduce that it will never occur.